Okay, so we left off in section 4.2, finding the slope of a line. And so far, all we really know is that a linear relationship can be expressed through a graph or potentially a table of values as well. But for sure, mostly all we've looked at are graphs. But in section 4.3, we start to analyze and look at how a linear relationship can be described through an equation. Okay, and so my first question that I'm going to answer is, why do we think it might be important to describe a linear relationship with an equation as opposed to using a graph? Well, as I mentioned here, um, an equation wouldn't be as tedious as making a graph. I think we can all agree that making the graph, the process of it, coming up with the scale, labeling it fully, drawing the points, it could be a very tedious task. And definitely, if we can come up with an equation, it can be a lot quicker. And so we would use the equation in the same way that we use a graph. We used a graph in Unit 2, we used it to do what's called interpolating and extrapolating, which was basically making predictions. When we were extrapolating, we were making predictions into the future using our graph. With our equation, we can do the exact same thing, only a lot quicker. Okay, so those are the two main reasons why it'd be more beneficial to use an equation as opposed to a graph. So now we have to come up with, how do we write an equation for a linear relationship? How can we figure out what best describes a line and then put that into an equation? So my next question is, looking at this line here, is what characteristics do you think would describe this line, kind of everything you would need to know about that line? And so I mentioned them here below. There's two things. We know that the steepness of the line is definitely going to be a factor here. And we know that in math, we call the steepness either the rate of change or the slope. Okay, so the slope or the rate of change definitely needs to be reflected in our equation if we're going to be describing our line in the equation. Secondly, we'll need some sort of position, some sort of starting point for our line, and that is listed here, is where it crosses the y-axis. That gives us the location of where the line should be placed. So if we have the slope and we have the location of where it crosses our y-axis, uh, those two characteristics should be enough information. It's pretty much everything we need to know about that line if we had to draw it. Well, it's the same thing with writing out the equation. Okay, and by the way, the location here, as I mentioned, uh, the part where it crosses your y-axis, where the line crosses the y-axis, remember this is your y-axis here, that is going to be called, and throughout this lesson I'll be calling it the initial value or the y-intercept. Okay, just like the slope, we can call it rate of change or the slope. Same thing with the y-intercept, we can call it the initial value or the y-intercept. And for this particular line, it would be right there. That's where it crosses. So it crosses at the point 0, 0. That's where it crosses the y-axis. Okay. So let me just kind of clear that out of the way so that we can write more on that. Okay. Oh, and by the way, the slope of this line, because this is going to come into play a little bit later in the lesson, the slope of this line is 2. Okay, let's keep that in mind. And in case we want a refresher from the last lesson, how did I get 2? Well, how did I get a slope of 2? I pick 2 points on the line. I draw my triangle. And I find my rise. In this case, my units are going by 1. So it's 1, 2, 3, 4, a rise of 4. And my run, again going by units of 1, is 2. And I know that the formula for rate of change is rise divided by run, which is 4 divided by 2, which is 2. So that's just a quick recap of our last lesson, but this is going to come into play. So remember this number 2. It is going to come into play very shortly. Okay. So we're starting to understand a little bit more of how to describe this line in our equation. So far we know we need a rate of change or a slope, and we need some sort of initial value to know where to position the line. All right? Okay, but now we just need to figure out the notation. How do we actually write this as an equation? And to do that, we're going to look at this table of values. Okay, so this is called a table of values here. And we are going to take a look at the pattern that is occurring here, or the relationship that is occurring from going from X to Y. All right, so we're going to take a look at this pattern. And by looking at it, what would you say is happening with all the Y values here? How are they related to the X value? So 1 and 2. And then the next point, 2 and 4. And the next point, 3 and 6. The pattern we see in this table is that all the Y values are twice the values of X. They're twice the values of X. So the Y's are twice the value of X. So how would we write that as an equation? Well, Y equals, it's 2 times the value of X. So 2 times our X values. That right there is a linear equation. All right? So you leave Y and X just as Y and X. You're not plugging in numbers for Y and X because there's many different possibilities for Y and X. So you leave those just as Y and X. And all you do is you write in the 2. All right? So all the Y's are twice the values of X. This is the first linear equation that we have made. And remember the slope that we found up here? Remember how it was 2? Okay. It is not a coincidence that this 2 also shows up here in our equation. Because this table, by the way, and I'm not sure if I mentioned this, but this table is actually all the coordinates for this line. Okay. So I just wrote down the coordinates. So here's one coordinate is 1, 2, then 2, 4, then 3, 6, and so on and so on. So I just wrote down the coordinates of that line into this table. And so there you go. That 2 pops up there. And again, it is not a coincidence that the slope is the same as this number here. It is not a coincidence. That will happen for every single linear equation. Okay, so now we notice that in this graph, our y-intercept, or our initial value, was 0, right? So 0, 0 was our y-intercept. Now, in the next graph, we notice that the y-intercept this time is moved. So I purposely drew a line that was shifted up. So instead of the y-intercept being here at 0, 0 and our line looking like this, it's a little sloppy. Okay, we actually move that line up. All right, now I still drew a line that had a slope of 2. So this, if we were to find the slope again, it would still have a slope of 2, a rise of 4, a run of 2. The rate of change would still be 2. Okay, so keep that in mind, that I drew the exact same rate of change. The only thing that I did was I shifted this line, which originally crossed the y-axis at 0, I moved it up to 3. Okay, so how would we write the equation of that line? It's still going to start with y equals 2x because it still has the rate of change of 2. Okay, so it's still going to be it's still going to be 2 times the value of x. The only difference is because we're shifting this graph up 3 units, right? It now just becomes plus 3. So the linear equation is still 2 times x, but then we're going to add 3 in order to get all our y values would be. All right, and that's what's written down here, exactly what's written here. Here's your equation for that line. It's the line of y equals 2x. It just shifted up 3 units. Okay, so that's about as involved as a linear equation is going to get. This is a linear equation. Okay, so was y equals 2x. That was also a linear equation. They're both linear equations. It just so happens that for this equation, it only has a 2x. That's because the y-intercept, instead of it being 3, it's just a 0. So realistically, we could have written it as y equals 2x plus 0, but I mean, you don't need to show the plus 0 there. Don't need to show it. So you would just write it as y equals 2x. Okay? But down here, because the y-intercept was 3, it's an actual value, we had to put plus 3. So any linear equation, okay, any linear equation can be generally described by this equation right here. And that is y equals your rate of change times x, and then plus or minus. I put plus or minus there because it could either be a positive y-intercept, but it can also be a negative y-intercept, right? Like our line could cross somewhere down here, right, where the y-intercept would be -5. So I put plus or minus there for that reason, the fact that it could be either a positive or negative y-intercept. So the rate of change times x plus or minus our initial value. And remember, another word for initial value is y-intercept. Okay, so we're going to try to stick with this equation here, just because it makes a little more sense to see the letters ROC for rate of change and initial value. But mathematically, okay, mathematically we don't use this terminology or this notation ROC or initial value. Instead, the mathematicians have come up with these letters to use instead of it. So instead of writing ROC, they call the slope m, or the rate of change m. And instead of using initial value, they called that the letter b. All right, those are just the letters mathematicians came up with. Obviously, it's a little bit more efficient than writing out the term initial value or ROC, just using the letters m and b. So y equals mx plus b is the exact same as this, just using different letters. Okay, so this is like the official equation here, right here. This is the official equation. We'll try to stick with this top equation just because it's a little bit easier to look at and know what to do, right? You see ROC and you know you have to find the slope. You see initial value, you know you have to look at the graph and find the y-intercept. Okay, so now let's actually, oh, and by the way, you don't have to use the letters X and Y here and there. You don't have to use those letters. You'll see that, like for example, in the last lesson we did distance time graphs. So instead of X and Y, remember what our labels were for on our axes. They were distance and time, or D and T. So you can use the letters D and T if you're dealing with distance and time instead of X and Y. Okay? And that goes for really any situation. It could be different. I mean, you could still just use X and Y, or you can change those letters if you want. Okay, so let's actually try an example, and that'll be it. Okay. So a linear relationship has a rate of change of 5. Okay, rate of change of 5. So I'm just going to make a note of that. ROC equals 5. And it has an initial value or y-intercept of 10. So my y-intercept is 10. So I'm just making note of that and writing that on the side. The question is, to complete the table, draw the graph, and then write out an equation for this given information. Okay, so I have started this table for you, and you're probably wondering why do I have x values written in with no y values? All right, it's because the x values, remember what the on the x-axis, that's our independent variable. So remember that our y values are the important thing here. Okay, the x's are independent. We can kind of make up whatever x values we want, but the y values we can't make up. Okay, because the y values depend on what the x value is. And that's why I just wrote these random numbers here in the x column. I just wrote out 0, 1, 2, 3. All right, I could have picked any other ones. I could have picked 0, 2, 4, 6 or 0, 5, 10, 15. It doesn't matter what you pick for x. I mean, to make it easier on yourself, go by ones. Okay, see how I went by ones here? I went 0, 1, 2, 3. That's just going to make it easier for yourself. But now we need to figure out what our y values are going to be based on this information given. So it says that the initial value, or the y-intercept, is 10, and then there's a rate of change of 5 after that. All right, so what value should I put in to this first spot here? If my x is 0, that must mean that I am on, if I look at my graph here, if my x is 0, remember this is my x-axis, okay, my x is 0, that means I'm right on the y-axis. That means that that initial value goes right here. That 10 goes right there. That's my initial value. It has to match up with 0 for x. So your initial value has to have a 0 for x. Otherwise, it's not your initial value. So it has to be 0, comma something. In this case, it's 0, comma 10. All right. Now, after that 10, we have a rate of change of 5. That means that our y values are going to increase by 5 for every increase of x. So y values, I'm just going to make note of that. Y values increase by 5 for every value, or for every increase in x. So now it's simple. We're just going to count by 5s for the y's, and we'll have this table finished. So 15, 20, 25. So for every increase in x, so we go from 0 to 1 in x, we go 5 up for y. Okay, then we go 1 to 2, we go 5 up more, 5 more in the y direction. Okay, and we've completed the table. I drew the points here for the graph already, guys. I mean, you guys would have just plotted these points. So 0, 10 is this point right there, right? This point here is 1, comma 15. This point here is 2, comma 20. And this point here is my 3, comma 25. I already put those points in for us just to, so I can save some time. Okay, I can't draw with a ruler on this, but I attempted to draw a straight line there. You would have to draw a straight line, so please use a ruler. Okay, and so we've done the graph. So we've done the table, we've done the graph, and now our last way, kind of showed the answer there, is to write an equation. And so I start by writing the general form, right, from the previous page. That y, for the equation of a linear relationship, it should look like y equals the rate of change times x, and then plus or minus whatever my initial value is. Well, I already said above here, we already know the rate of change. It was given to us in the question, right? Right there. That's nice. And we know the initial value. That was given to us in the question. It's 10. Okay. And so all I did was I wrote in the rate of change of 5 there. I put in my initial value of 10 there. And notice I keep, because this is a common mistake, so pay close attention here. Keep x and y just as x and y. Don't put in numbers for them. You just keep it as x and y because they could be a number of values. I mean, look at all these x values it could be, or all the y values, and this would go on to infinity. So you don't just put any x or y, you just leave it as x and y because it can represent so many different values. All right. And then the last thing, so if our equation is y equals 5x plus 10 or 5 times x plus 10, look at what I've put here just so you can make your connection between this, all three ways of representing the linear relationship. I put this equation says the value of y, okay, so my value of y is 5 times the value of x plus 10. And I mentioned here, take a look at your table of values and verify if that's true. Okay, so 5 times the value of x plus 10. That's what all our y should be. Let's go to our table and let's just do that and check that. Okay, not that you have to do this, but in case you didn't believe me that this table and this equation represent the same thing, we're going to verify that right now. They represent the exact same linear relationship. So my y value, let's do this y value right here, 15. My y value should be 5 times my x. So if my x is 1, 5 times 1 is 5. And then it says plus 10. So I was at 5, right? 5 times 1 is 5, plus 10, and what do you get? 15. So this equation works. It works. It matches with this table, and we can try it even for 25. Let's try it for 25. So if my x is 3, do 5 times 3, which is 15, right? And then add 10, and you get 25. So you can see that there's this relationship between x and y, and we've described it in all of these different ways, in all three of these ways: a table, a graph, and an equation. And they all describe the exact same linear relationship. They're just different ways of describing it. Okay? You can see the advantage of the equation. If you get good at it, it's a lot quicker and easier. It's a quicker way to describe a relationship as opposed to doing a table of values or as opposed to doing a graph. It's just a much quicker, more efficient way. All right, so that concludes this part of the lesson, 4.3. There's going to be a second part. It's going to be significantly shorter, but I'm going to discuss and describe something called partial and direct variation. There's quite a few questions in your homework on that, and so I'm going to do a separate short video on that just to show you what the difference is between a partial or direct variation.